Oh no, now I've stopped recording. Okay, we're recording again. Oh my God. Alrighty. So calculate the concentration of the chromate ion in a saturated solution of CaCrO4. Are we going to use the solubility equilibrium equation or the precipitation equation? Are we doing a precipitation reaction or a titration? No. Are we doing something with KSP? Yep. So we are going to use the SEE. And you guys get to remember if that's a one-way arrow or a two-way arrow, and if the solid goes on the left or the right. So write that out for yourself and check with your partner. I would be tempted to get another piece, like an extra piece of paper, because I don't think this does it justice. Whoops, what am I doing? Did you use an equilibrium arrow?
Yes.
Did you put the solid on the left?
Yes.
Excellent. And did you include your charges? And did you include your aqueuses? Yay. Okay. Now we need to calculate the concentration of the chromate ion. Yes? So we're starting with, we're putting some solid into water. How much dissolved stuff do we start with when we have solid in water? 0. Do you think you'd be able to solve the rest of this? You want to find the concentration of the chromate ion.
No.
Did you guys come up with that? The plus X?
Yes.
Yes. Okay, good. Phew. Because there's nothing really else to do, is there? Because you're trying to find concentration of the chromate ion, which is this one. Yeah?
Yep.
Do you know what to do next? Write the KSP expression. Yep. KSP equals.
X squared.
Not yet.
Oh.
Just like in Ka, you cannot get away with just throwing the x squared there right away. You have to show the expression, the KSP expression. Yeah, I don't know. It kept giving me a downward line for some reason. Is good?
Yeah.
Yes. Now, yesterday, we learned a new word, and that was on page 26. We learned the word molar solubility. Yeah? And molar solubility was how much dissolves. What's another way of saying how much dissolves? Concentration. So the molar solubility is how much dissolves. In the question yesterday, it was how much lead iodide dissolves, right? Because that was what we were dealing with. We were dealing with the molar solubility of lead iodide. All right, and if you recall, the solubility was 1.52 times 10 to the minus 3, and this was a 1:2 ratio, so we got those numbers, yes? Okay, so what if, on this question here, what if instead of saying, calculate the concentration of the chromate ion, what if I said to you, what is the molar solubility yeah, but it's not just the concentration, it is the concentration of the saturated solution. Yeah, it contains because this is you're saying how much can dissolve? Yes? How much can dissolve? That's the maximum concentration, right? If you dump this into water at 25 degrees Celsius, this is how much will dissolve, no more. Okay. Maybe less if you don't put enough in. Okay. But that seems unlikely because it doesn't dissolve very much. It's like 7.08 times 10 to, it's like 0.02. Okay? So what is the molar solubility of CaCrO4? And remember, molar solubility is how much will dissolve. In other words, molar solubility is the concentration of chat with your neighbor about that.
Oh. Yeah. Oh, yeah, that is a solid.
Yes. We don't need that. We're not diluting anything. M1V1, M2V2 is for when there is a dilution. We have not diluted anything. We took some water, we dumped some solid in it. Yes.
Would you multiply by 2?
Well, let's think about it. Let's start with HCl. Yes? If I told you that the concentration of HCl was 1.5 molar, then what is the concentration of H plus? 1.5 molar. And what's the concentration of Cl minus? 1.5 molar, and that is because the ratio of these things is 1 to 1 to 1. So if I tell you, well, you just calculated that the concentration of chromate is 0.0266 molar. What is the concentration of CaCrO4? It's not a difficult question. It is 0.0266, yes. So we're good? Yeah. Now, often what I'll do is I'll put this in brackets here because can you have a concentration of a solid? No. So when I'm writing it under the solid, I say that. But if I were to make this solution, I would not walk around and say, the concentration of the calcium and the chromate is 0.0266 and the concentration of calcium chromate together is 0. Right? Well, it is 0, but the concentration of hydrochloric acid is also 0. Yes? But I don't say that. I say I put 1.5 moles of HCl into 1 liter, so the concentration of HCl is 1.5. Yes? I don't care what it did afterwards. Yes, it completely dissociated afterwards. Yeah? So the concentration of HCl is 1.5 molar. How much of the calcium chromate managed to dissolve? 0.0266 moles per liter. So that's how much I say the concentration of calcium chromate is. That's how much managed to dissolve. Yes? And that's the reason why whenever we talk about the concentration of a weak acid, we're always talking about the initial concentration because it's the same principle. If I had CH3COOH, what's the name of that acid, by the way? That is acetic acid. You should know that name. Okay? It's the commonest weak acid ever. Because it's just vinegar, right? Just vinegar. All right. Huh? Ethanoic acid. That's its official name. Yeah. So, if I have this thing and it dissociates into H plus and CH3COO minus, but I put 1.5, if I say I've got a concentration of CH3COOH, that means I dissolved 1.5 moles in 1 liter. I don't care how much dissociates. That's how much dissolved. Some of it doesn't dissociate, some of it does dissociate, but that's how many moles of it I put into 1 liter, and that's how much dissolved. Yes?
So how would you say, how would you describe the solid? Because these are acids.
You don't. You just say the concentration of calcium chromate is 0.0266 molar.
Even though it's not really.
Well, it is.
But
But that assumes that you're a chemist and you know that when I say that, that's how much is dissolved. So that's floating around as ions. No, but you just have to assume that the person you're talking to knows that's what you mean. Yeah? Yeah. Are we good? Excellent. Okay. So that takes us to there. Back to our KSP. So if we have a smaller KSP, what does that tell us about our ion concentrations? Yeah, so if we have the smaller the constant, the fewer the ions. And what does that tell you about the solubility, about how much will dissolve? It's going to be less soluble. The solubility is lower. Solubility is lower when KSP is smaller. Yes? Compounds that are extremely water insoluble will have KSP values on the order of 10 to the negative 30, 10 to the negative 50, or even smaller. Crazy. Okay, so if I give you a series of compounds and I say which is the most soluble, like let's say I gave you, say I gave you MgCO3 and I gave you FeS and I gave you AgCl. Which of those is the most soluble? And they are in alphabetical order, so you can look them up in alphabetical order. What do we know about AgCl that would help us here? Okay, can we quantify that? We know it's KSP, right? So we could say, the KSP is 1.8 times 10 to the minus 10. Iron sulfide, 6.0 times 10 to the negative 19. And magnesium carbonate, 6.8 times 10 to the minus, is it 6? Yeah. So out of those three, which is the most soluble? This is the most soluble. Who's the least soluble? Least soluble. Now, it's going to become more complicated if you have something where you do, these are all 1-to-1 salts, right? The ions are 1-to-1. If you have a 1-to-2, your KSP expression is no longer going to be, this would become X and this would be X, this would be X and X. So they'd all be KSP equals X squared. Yes? For the ion concentrations. But if you have something where you have 2-to-1, it becomes a little bit different. So you can only do this kind of easy comparison when you have the same ion ratio. Okay, don't worry about that too much. We'll talk more about it later. Okay, but that it gives you an idea that the bigger the KSP, the more soluble it is. The lower the KSP in general, the less soluble it is. Oh, and we're going to talk about it right now. I didn't realize it was right here. So here are the ones we just did had a 1-to-1 ratio. These ones all have a 2-to-1 ratio. Yes? We have KSPs for them. In the Ag2CO3, we have 2 Ag to 1 CO3. In BAF2, we've got 2F for every 1 barium. And for lead hydroxide, we have 2 hydroxide for every 1 lead. So they're all 2-to-1. It doesn't matter whether it's the first one that's 2 or the second one that's 2. So far, so good? Okay. Because what we know is that, whoa, what happened? There we go. What we have is I call it an A2B kind of salt. Okay, A2B, solid. If we write the solubility equilibrium equation, what would I get as my product? Two A plus. B2 minus. Yes, absolutely. Now, if I say that the concentration of A2B is X, let the concentration of A2B equal X. Yes? So that means that underneath my A2B, I can write X. I put it in brackets because it's a solid, yeah? What's the concentration of A? 2X. What's the concentration of B? X. What is my KSP expression? Wait, the expression.
A plus squared.
A plus squared times B2 minus. And then if we plug our x's in, what do we get? Yeah, we get 2x all squared times x, which is going to give you 4x cubed. So anytime you have a 2-to-1 ratio in your salt, KSP is going to equal 4x cubed. And what is x? X is the concentration of the A2B, of the 2-to-1 ion compound. Yes? What's another word we can use for that concentration of a low solubility compound? The molar solubility. Okay, and when we say X, that's going to be X molar. Yes? All of these things are molar. So anytime you have an A2B salt, you're going to know that KSP is equal to 4 times the solubility cubed. Yes? Yes? And normally what we'll do is we'll say, because that's awkward to write, KSP is equal to 4x cubed, where x is the molar solubility. Now this is lovely, beautiful. Use this to death in the multiple choice section, yes? If you were doing a written response, would you want to skip the steps in blue? No. Okay? In written response, you need to have that part there. And you also need to have this part here. Yes? So you would say, let the molar solubility of A2B equal X. And don't worry, I'm gonna stress this again and again as we go through. In a written response question, you would get like 0.5 marks for this. You would get 0.5 marks for this. You would get 0.5 for this. And then everything after that is gravy. Yes? Let the molar solubility of A2B equal X. And you should say let there. Or you can say let the concentration of A2B equal X. That's fine too. Okay? Pardon me? No, you can have more steps. You just can't you can't skip writing the KSP expression, for example. Because people do, they're like, I know KSP is equal to 4x cubed, bam, off I go. Because it's easier, but you want to prove that you know where that came from. Do you know what I mean? And you would also show this, right? You would say, I'm going to show you my dissociation equation, my solubility equilibrium equation, and I'm going to show you the ratio of the x's there. Okay, so you should show like all of that stuff. Don't worry, I've got it somewhere else. I've got it all written out. Like you get marks for this and this and this and this. This is just an introductory. Okay, so it's laid out a bit better a little bit later on. Now going back, because these all have the same ion ratio, their solubility compared to their KSP will all be the same. You will find them in the same way. So solubility would equal KSP divided by 4 cube root. Yes? So you find it all the same way. What that means is the bigger the KSP, the bigger the, what is X? Molar solubility. The concentration. So as long as you've got salts that are all the same ratio and you're finding X all the same way, then you can compare their KSPs and say, yes, 10 to the 6 is the biggest. Therefore, BAF2 is the most soluble. Yeah, this is just to verify that you can directly compare their KSPs and get at their solubilities. You would actually have to do the math. So if I gave you, let's say I gave you Ag2CO3 and I gave you AgCl. Right? Now I have ratios that are different and I would actually need to do the math on them to find the actual X value. So in this case, KSP would equal X squared, right? And for this one, KSP would equal 4x cubed, and you'd actually have to solve for X in both cases. Yeah?
Like, and how, you show how if you have a ratio to the volume of the
If I have a ratio 2 to 1 and 1 to 2, what?
like, why is it the same? Like, why does it not matter if it's 4?
Oh, if I have 2 to 1 and 2 to 1?
Yeah, 2 to 1 and 1 to 2.
Oh, then I need to do the math. If they're all the same, I don't have to do the math because the math is all the same. So I can say for every single one of these, if KSP is bigger, then molar solubility will be bigger because I calculate them all the same way because they're all something squared times something. x squared times 2x squared times x. Okay? Right now, you don't have to worry about doing this solving bit. We'll do that later. Okay? For now, what you should know is you should be like, you have given me all salts with 2's in them, and the other one's a 1. I can directly compare those KSPs and say, which one is the least soluble? Who is the least soluble of these 3 salts? Who is the least soluble? PB? OH2, because its KSP is the smallest. So don't get too wound up about the math right now. You've seen the math. Just let it kind of wash over you. If you got it, that's great. If you didn't, don't worry. There's a whole section in 3.3 devoted to the math. Okay, so the math will come back. All right, right now you're just like, okay, there was some math, but it just tells me as long as I have the same ratio of ions, I can directly compare KSPs and get the relative solubilities. And there's no math involved in that, okay? So, in other words, you can compare KSPs directly to determine relative solubility. It works only for compounds with the same ion ratio. So you could do these 3 because the ion ratios are the same. They're all 2 to 3. You can use compare KSP to find the relative solubility. You don't have to do any math. You can compare AgCl, calcium carbonate, and lead sulfide because these are all 1 to 1, 1 to 1, 1 to 1. Do you guys know what I mean when I say relative solubility? Tell your partner, what do I mean when I say relative solubility? What does relative solubility mean? Yeah, it's just comparing their solubilities, which is the most, which is the least. Okay, so that's all it is. Could you compare silver chloride, CaOH2, Mn3PO42?
What? No.
Not yet. Not yet. Requires math. Okay, we have a little thing on writing KSP expressions. Oh yeah, here we are. We're breaking everything down. So each step is worth 0.5 marks. So you write the dissociation equilibrium equation. I should say the solubility. Oh, actually, that's okay. Dissociation also works. You could call it the D, but I like the C better. Okay, so it is the solubility equilibrium equation, the C. So you get 0.5 for this. Do not skip this step. If you skip it, you lose 0.5 marks. Write the KSP expression. That means, what would the KSP expression be? Yeah, you need your square brackets, you need your Ca2 plus, you need your CO3, 2 minus, okay, that's worth 0.5. Hello. Who we got today? Brian, yes, thank you. Okay, so if you were asked to write the KSP expression for MgOH2, you should show this for 0.5, and you should show this for 0.5. Yes. Okay, there's some questions. We'll leave those for later. We're going to move now to page 30. We are now looking at saturated and unsaturated solutions. See if you can tell your neighbor if you know what those two things are, saturated and unsaturated. What are you doing on your phone, Tony? Checking the thing. Okay, what do we mean if it is unsaturated? Not saturated. What does saturated mean? If a sponge is saturated, what does that mean? It has its max volume. So like the sponge contains the maximum amount of liquid it can. It is saturated. Yes? So if we have a solution which is saturated, what does it mean about that solution? Yeah. Yeah, you've dissolved the maximum amount possible and you cannot dissolve anymore. You can keep throwing solid in there and stirring and nothing more will dissolve because you've already hit the maximum. Yes. When you make what?
When you increase temperature, you can
yes. Yes.
Does that mean like when you increase temperature, KSP increases? So it's like it dissolves more?
Because normally, most times, dissolving is what kind of a process? Endo or exothermic? Mostly it's endothermic. There's an occasional exception to that, but not, like, very rare. Okay, so if you increase the temperature, you're going to increase the KSP, which increases the solubility. Yeah. Okay, so if you have an unsaturated solution, that means it does not contain the maximum yet. Okay, so it is a solution that contains less than the maximum amount of dissolved solute. Now, if you have an unsaturated solution and you have some undissolved solute present. So if you have an unsaturated solution and some undissolved solute is present, Is the system at equilibrium?
No.
No. Okay. And if you have undissolved solute and we're not yet at equilibrium, is the rate of dissolving slower, faster, or the same as the rate of precipitation? So imagine you've got AB, solid, A plus B minus, but we are not yet at equilibrium, right? We do not yet have the maximum amount of dissolved ions. The rate of dissolving is going to be faster than the rate of recrystallization, because that means you're going to be able to dissolve more and more and more until you hit the equilibrium. Yes? Or until you run out of solid. That's the solute. That's the other possibility. You may hit the end of your, like you may run out of solid before you get to equilibrium, right? And then there is no equilibrium because there is no solid. Yes? So that's like salt water, right? There's no solid salt there, right? If you get some ocean water, there's no salt hanging out in there, right? Solid salt. Okay, so our rate of dissolving is greater than the rate of precipitation, and you can see this is dissolving. And this is precipitating. Or you can call it recrystallization if you prefer. Are you asking if we already have a saturated solution and we put more solid in, or you say we're starting from like just water and we dump a solid in? Okay, so starting from water, all right, what's going to happen is that, let's say we just dump this into water, okay? This stuff just went into the water. Okay, so now we have, at the very beginning, there's no solid present, or sorry, there's no dissolved ions present. That's what I meant to say. So you're going to have a bunch of things coming off. Now, because this is a system where the moment you have stuff in the water, it can then reattach because it's an ion. It's going to be attracted to the other ions that are nearby. Yes? So you'll get dissolving and you'll get recrystallization, but the dissolving process is going to happen more frequently than the recrystallizing process. Okay? And you will end up, until you have saturated this solution, it's going to continue that the dissolving is faster than the recrystallization. But as you saturate it, you're going to get more recrystallization. Yes? Don't draw this on your picture. It makes the whole thing yucky.
Starting off, you have like this thing going into the water, but it's just dissolving, and then once it's joined in, like the stuff, it goes to like become solid again.
Yes, although it becomes solid even when there is not too much already, even when it's not full.
So when you say recrystallization, they're like.
So, like, you've got.
Just like a wall.
The rate of dissolving initially is fast, and the rate of recrystallization is 0. Yes? Because this is an equilibrium, What's going to happen to the rate of dissolving as time goes on? It's going to go down. And what's going to happen to the rate of recrystallization? It's going to go up. And eventually, what's going to happen? The two are going to be equal. Now, why does the rate of recrystallization start going up? Because you actually have some ions that could recrystallize. At the very beginning, there's no ions to recrystallize, but as soon as you get some dissolved ions, they can recrystallize because it is a reversible reaction. Tony, did that make sense? Or were you too busy packing up to listen to the explanation I did entirely for your benefit? It's been recorded. You can listen to it. Maybe after the test. Your homework is to study for your test. I will see you tomorrow. I know there's like a BD SFU thing tomorrow at lunch, but
Tomorrow?
if what? Yes. Be here on time. Like, don't be late because you get to start when you get here, basically. Okay?
But I thought the BB thing was at lunch.
It is at lunch.
But we're second.
Oh, yeah, I know. I don't know. I'm trying to say that if you feel like you're going to need 10 minutes of extra time, you either need to have that 10 minutes before class starts or after class is over. So you need to make a choice. Yes? Hi.
Right, so basically, it's like I'm not like put something to let it dissolve.
But the moment you have two dissolved particles, they could rejoin.
So it's not. It's just like when you have one, no, it's not gonna recrystallize. When you have like two, like yeah. The more dissolved particles there is, the more chance it will crystallize. That's why dissolved rate decreases.
Yes.
All right.
Yes.
Yeah.